Hello Comets! Today we're going to be discussing a topic called McLafferty Rearrangement. This is a concept that you'll see a lot with mass spectrometry, so let's just do a quick review of how mass spec works. So basically how it works, you put a molecule, so say we have 2-pentanone here, we put this molecule into our mass spec machine. What our machine will do is it'll rip an electron off of this molecule, turning it into our parent ion, or M+ peak. Your parent ion is very unstable, so it's going to break up into two pieces, a cation and a radical. Our mass spec machine will detect our cation, and the cation peak that we end up with are all these peaks that we see here with numbers on top of them, which these numbers represent the mass that our cations weigh in AMUs. The different ways that our molecule can break up into two pieces are called our types of cleavage. And we have three common types of cleavage: alpha cleavage, dehydration, and McLafferty rearrangement. The one I'm going to be discussing most today is McLafferty rearrangement. So let's say we had a question on an exam that was asking us to find the fragment that has an M/Z ratio of 58 for 2-pentanone. What this question is basically asking me is which fragment has a molecular weight of 58 AMUs. In order to answer this question, I'm going to first try out some of our more straightforward common types of cleavage. A great example is alpha cleavage. And the reason I'm doing alpha cleavage is because that just makes the most sense, being that we have a functional group. We have a carbonyl, and alpha cleavage is simply just cleaving one carbon away from our functional group on each side. So I'm going to draw out what all of those fragments look like, which, remember, on MS, when you cleave, one fragment will show up as a radical and one will be a cation. So these are our fragments if I cleave from the left side. Now I'm going to draw out what our fragments will look like if I cleave from the right side. So these are our two possibilities of fragments that we could get when cleaving from the right side. And something that we definitely have to remember is that on MS, only the cations are picked up by the machine, not the radical. So all these peaks that you see here are all cations, not radicals. So now what I'm going to want to do is calculate the molecular weight of all these peaks. So this one weighs 71, this one's 15, this one is 43, and this one's also 43. Since none of these peaks weigh 58, I know that you cannot determine this peak through alpha cleavage. I also know you can't determine it through dehydration because we don't have an alcohol. So now I'm going to try McLafferty rearrangement. So let's take a look at how McLafferty rearrangement works. The most important thing is that McLafferty rearrangement requires a carbonyl with a gamma hydrogen. So we need a carbonyl, which we have here, and we need a gamma hydrogen, which is a hydrogen that's 3 carbons away from our carbonyl carbon. So we look 1 carbon away is alpha, 2 is beta, 3 is gamma. So this compound could undergo McLafferty rearrangement. So let's take a look at how the mechanism behind McLafferty rearrangement works. This mechanism is going to happen in a few steps. The first step is that these electrons, these pi electrons between oxygen and carbon, are going to come up onto oxygen. So what we're left with is an oxygen with a negative charge and a carbon with a positive charge. A negatively charged oxygen is actually a good base, and bases extract hydrogens. So what this negative charge will do, what this lone pair will do, is go out and snag a gamma hydrogen. So if we look at what that looks like after that's happened, so our oxygen has snagged our gamma hydrogen, but something that I want to point out is that these electrons between hydrogen and carbon are still there. So they need to go somewhere. So what we're going to do is we're going to make them form a pi bond, a double bond with our beta carbon. And I'm going to draw out some of the hydrogens as well. And color code this for you guys. So something that I want to point out for you, I want you to look at this carbon that I'm dotting in red. This carbon right now, as it is, has 5 bonds. 1, 2, 3, 4, 5. Carbons can have a maximum of 4 bonds. This right here is violating carbon's octet rule. So what we're going to have to do is get rid of 1 bond. So what I'm going to do right here, I'm going to cleave the bond that's between the beta carbon and the alpha carbon. So if I look at what that looks like, these electrons right here are the electrons that I cleaved off, and they need somewhere to go. And I see that there's a positive charge here. Positive charge represent a deficit of electrons. So this is an amazing place for these electrons to go because they can be used to fulfill that positive charge and make it neutral. So these are our 2 fragments that we're left over with. And just so that you know, on the MS, the way that you would denote these fragments, say that this alcohol fragment is the fragment we're going to want to look at on our MS, you would denote it as brackets with a positive and radical at the top of it. So let's draw out how this mechanism looks like in real time so that we can see how all the electrons are moving and what's happening. Which I'm not going to draw out all the hydrogens here because they're not all super important. So the first step, our electrons, our pi electrons between oxygen and carbon are going to come up onto oxygen, leaving our oxygen with a negative charge and leaving our carbon with a positive charge. This negatively charged oxygen is a good base, so we're going to use these electrons to extract our gamma hydrogen, leaving us with an alcohol and with 2 electrons that now need somewhere to go. These 2 electrons are going to be used to form a pi bond with our beta carbon. And now when we look at our beta carbon, it has too many bonds. It has 1, 2, 3, 4, 5 bonds. Something needs to break, so I'm going to cleave the bond between the beta carbon and the alpha carbon. And after I do that, these 2 electrons that used to be in that bond need somewhere to go, so I'm going to use them to fulfill this positive charge and make it neutral. So those electrons come on to what used to be the carbonyl carbon. And these are our 2 fragments that we're left with. Once again, if you would want to denote it in your MS, you would denote it with brackets and a positive and radical at the top right of it. So let's take a look back at our mass spec and see if the fragments that we got through McLafferty, if any of them weigh 58 AMUs. So I've drawn out our 2 fragments. Let's say I want to look at this fragment. Let's say I want to say this one could possibly weigh 58. When I calculate the molecular weight, turns out this one actually does weigh 58 AMUs. So this tells us that we were able to solve for which one had a 58 M over Z value through McLafferty rearrangement. So to sum this up for you guys, I've drawn out a sheet basically describing the summary of what happens in McLafferty rearrangement. Feel free to screenshot it, whatever you need to do to help this make sense to you. If you have any questions, make sure you ask any of the tutors at Peer Tutoring. We're more than happy to help you. Have a good day, guys. Stay safe.